This is the problem about two charged objects. One is positively charged, one is negatively charged. I'm going to start with my sketch. Let's see. I've got a positively charged object, and I've got a negatively charged object. And I know the quantities of the charge. I'm going to call this Q1. I'll say that Q1 is positive 2 times 10 to the negative 9th coulomb. And this will be charge 2. Charge 2 is negative 4 times 10 to the negative 9th coulomb. And they tell me the distance between them. This distance is 0.3 meters. And that's all that I'm given. Okay, so that's my sketch. Next it says, draw the E-field lines and equipotential surfaces surrounding the objects. Okay, I'm going to do this. I hope it's not going to look terribly messy. I'm going to draw it right on top. I think I'll use the color green for my E-field lines. All right, E-field lines point from positive charges to negative charges. I know I'm going to have this one E-field line in the middle that's going to point straight from the positive charge to that negative charge. And then I know I'll have another line that's going to go around and curve towards this negative charge. And I'll have another one that curves around to this negative charge. And then I'll put one out to the left side over this way. Right, my lines point away from positive charge and towards negative charges. So these lines represent the magnitude and the direction of the E field surrounding these charges. Right, these charges do something to the space surrounding them. There is an electric field surrounding these charges. This is one way I can show this electric field. This is called the E-field lines. All right, but I'm not done because charge 2 has twice the magnitude of charge 1. I'm going to need 2 times the number of E-field lines going into it. So charge 1 has 4 lines. I need to add 4 more lines. I think I'll do it this way. Here's 1, 2, 3, and 4. Oh, you know what? It doesn't matter where on the line you put these arrows. Let me just be consistent. I'll put the arrows right in the middle. Right, those arrows just show us the direction. Whoops, whoops. Well, all right. We've added that back in. Okay, so 2 times the charge should give me 2 times the E-field strength. That's why charge 2 has twice the number of E-field lines coming into it. Okay, great. I did my E-field lines. Now I should draw equipotential surfaces. Okay, this is the other way that we could describe the electric field surrounding charged objects. Okay, there's 2 ways to do this. E-field lines, E-field and force go together. They're related, right? Force is E-field times Q test. And then this is the new concept from this week, is these equipotential surfaces. Potential and potential energy are related, right? Potential energy is potential times Q test. E-field lines relate to force. Equipotential surfaces relate to potential energy. Let me draw these now. Okay, I'm going to remind myself that the formula for potential is KQ over R. And so I I realize that the sign does matter. The size of the charge matters, and the distance from the charge matters. I'm going to first draw where the potential might be 0. The potential might be 0 somewhere right in between these charges. In fact, and this has to do with this next question. The sum of the potentials is going to be 0 if the potential due to charge 1 equals negative the potential due to charge 2. That's going to happen somewhere in between the charges. It's going to happen closer to charge 1 because charge 1 has a smaller charge. I'm just going to draw this line. This is going to be where that potential is 0. We're going to calculate exactly where that is in a moment. And what that means is anywhere on that line, our potential is 0. Now, let me continue with these equipotential surfaces. They're going to look curved. I think I'm going to draw a nice big curved one here. Now here, the potential is going to be something positive. That's because it's closer to this positive charge. Potential does depend on sign. You can have a negative potential, just like you can have negative potential energy. Okay, and let me draw some around our negative charge. Here's what they look like. Here's one nice and close. These equipotential surfaces around the negative charge are going to be more closely spaced because this is a stronger charge. Let me just get a couple more in here. Okay. So everything to the left of that 0 line, this is going to be where my total potential is negative, and this will, oh, I just flipped that around. That'll be where my total potential is positive, and this will be where the total potential is negative. Okay, equipotential surfaces show surfaces where anywhere along the surface the potential will be the same. Okay, cool. Next, part 3 says determine A, the potential at a point halfway between the objects. Let's go ahead and do that. The potential at a point halfway between the objects. Well, what I need to do is find the potential due to charge 1 and the potential due to charge 2 and add them up. So I want to find the sum of the potentials halfway between. All right, well, the sum of the potentials will be the potential due to charge 1 plus the potential due to charge 2. And the formula for potential is K, that'll be Q1 over R1 plus K Q2 over R2. And I know all these values, so let me put them in. K is 9 times 10 to the 9th Newton times meters squared over Coulomb squared. Q1 is positive 2 times 10 to the negative 9th Coulomb. And R1, this is for the distance halfway between the charges, so that's going to be 0.15 meters. And let me put my values in for potential due to charge 2. Charge 2 is negative 4 times 10 to the negative 9th Coulomb. Notice sign matters. Okay, and that'll be 0.15 meters. Cool. Okay, and then if we punch it into a calculator, let's see. That 10 to the 9th thing cancels, so I'll just do 9 times 2 divided by 0.15. That's going to give me 120. My units are going to be volt. I'll do my unit analysis in a moment. And let's do this for V2. So I'm going to do 9 times -4 divided by 0.15. That's going to get me -240 volts. So if I add those together, I'm going to get -120 volts. So that's the potential right smack in between the two charges. Let's do a little unit analysis. Okay, I see that one of these meters will cancel, and one of these coulombs will cancel. So I'm left with a Newton times a meter over a coulomb, which is the same thing as a Newton times a meter, that's a joule per coulomb. That's the same thing as a volt. That's what a volt is. So it's electric potential energy per unit charge. Electric potential energy per unit charge. That's the meaning of these units. Okay. Let's do part B. Part B says, where the electric potential is 0 other than far away. Okay. So let's find, where is the electric potential 0? I did draw that on my equipotentials. So we're looking for a spot where the sum of the potentials would be 0. Okay, well the sum of the potentials is V1 plus V2. And so if V1 equals negative V2, then the potential will be 0 there. So now let me put in my formulas for potential. That's going to be K Q1 over R1, K Q2 over R2. Okay, what I want to find is these R's. We're trying to find where this might occur. Let's see. These K's will cancel. I know these Q values. Let me put them in there. Q1 is going to be positive 2 times 10 to the negative 9th coulomb. Q2 is negative 4 times 10 to the negative 9th coulomb. So I'm comparing these two fractions, and I see, okay, on the right side I have this double negative, so that'll become positive and I don't have to worry about sign. Also, this 10 to the negative 9th, that would cancel. Okay, so I have these two fractions that I'm comparing. I think I'll write it again one last time. Really comparing 2 over R1 must equal 4 over R2. So for these fractions to be equivalent, R2 has to be twice the size of R1. Now I see these two charges are 0.3 meters apart. So what value could R1 be, and then what would R2 be if it's twice that value? Here's what I'm going to suggest. What if R1 is 0.1 meter and R2 is 0.2 meters? R2 is twice the distance of R1. And we could just double check it in this little fraction, make sure that it works. 2 over 0.1 meter, 4 over 0.2 meters. Okay, 2 over 0.1 is 20, and then 4 divided by 0.2 is also 20. So there we go. That must be the distance. And that is what I expected, that we're going to have a potential of 0 closer to that positive charge. Okay, so it says show all work, explain your thought process in words. I think I'm going to do that right now. I did explain it verbally. But let's do it in words. Written, I guess. So my thought process. For part A, my thought process was to find the potential halfway between the charges. I'd have to add the potential due to each charge. So let me write this in there. To find the potential at r equals 0.15 meters, calculate the potential due to each charge and add together. That was my thought process here. And let's write a thought process for part B. The potential is 0, where the potential due to charge 1 cancels the potential due to charge 2. Okay, and now evaluate my solution. How do you know whether your answer is reasonable or not? So let's look at part A first. Is it reasonable that right between the two charges, the potential would be negative 120 volts? I would say that this is reasonable. It's reasonable to get a negative answer, a negative potential, because Q2 is negative, but larger magnitude. Than Q1. And then this second answer, I would say that it's reasonable that the potential would be 0 closer to charge 1, because charge 2 has a bigger magnitude. So this is for part B. It's reasonable that the potential is 0 closer to Q1 because Q2 has a larger magnitude What I mean is that R1 will have to be less than R2. And that's it.